Thanks for the introduction. So, flood modelling. I've been involved in flood modelling for, it's now actually more than 30 years, and I've really seen the benefits that modelling flooding can bring to flood risk management. And I'm really pleased to be able to share some of my knowledge with you this morning. The focus is it's a high level presentation, so it's not, if you already know an awful lot about modelling, you may well get bored of this. It is a high level introduction to flood modelling. I'm going to focus on river flood modelling, although a lot of what I'm say applies to coastal flooding and stormwater flooding, surface water flooding. And I'll start by giving a little introduction about why flood modelling is necessary, the benefits of it. Then go into some of the terminology, an overview of what flood modelling involves, the modelling process, and then I'm going to give a few minutes on an example bit of flood modelling software just to bring it on and make it a bit more live and real for people. So flood modelling, why is it needed? Well, it's needed because it now underpins so many aspects of flood risk management. On the screen is some bullets and some pictures of some of the aspects of flood risk management that is the benefits from flood modelling. So for example, flood warning. So to define flood warning areas, modelling is used, and then more importantly, to do the predictions of what water levels or flows will occur at different points within a system. The forecasting of flows is done by modelling. And also by some observational data, but it's the river modelling that enables people to make more accurate predictions of when particular water levels will occur at different points within a system, which then feed into warnings that are sent to the public and other people. It's used to help identify where interventions are required, interventions being such things as building flood defences and other types of flood risk management activities. To then go through the process of appraising options, working out what is the best scheme in terms of benefits and maximising benefits and minimising costs, then fine-tuning the design of that optimum scheme. And then once something is in place, it helps also in the asset management process to help understand where what would be the consequences if a particular asset, a flood defence, a flood embankment failed, to then prioritise inspection and other forms of maintenance to make sure we're spending the money on maintenance in the areas that gives us the best benefit. It's also used for zoning the floodplain to help guide development, particularly the appropriate type of development in different areas, either away from the floodplain, or if it has to be in the floodplain, to make sure there's things are built off on high off the ground or with access routes or whatever it needs to be, to make sure if there is development on the floodplain that is appropriate. It's used, the flood mapping that's produced from flood modelling is used to raise awareness of which areas could be subject to flooding in the future. So this could be used as you're looking at properties and looking at trying to work out where to buy properties, and for many other aspects of raising the activities that people can put in place to better protect them against flooding. And there are a range of other things that modelling is used for, including sort of high level investment aspects to do with working out how much money government should try to give to this area or other funders should give to it. Modelling is used to understand the pros and cons of different investment levels, as an example of one of these other areas. So what is flood modelling? Well, essentially, nowadays it involves using computers to predict what the water levels and flows in the channel system or on whatever network you're looking at, and the flood depths on the floodplain are, for a range of different scenarios, if you like, which can be different amounts of rainfall or different extreme tides, looking both now and into the future with climate change, and then with different setups on the floodplain, with and without interventions and this type of things, without development. So it's using computers to help you predict what would happen if, and then there's lots of things that you can assess under that scenario analysis. It's a model, and that's the key thing. It's a model of the real physics. Even the most complicated model is only an approximation. There's a range of different types, ranging from very simple models, which could be just a horizontal projection of a water level in the channel or in the sea across the floodplain, through to what are called full solution methods, where they try to apply as much of the physics of the processes as they can. But in any case, it's still a simplification because the mathematics is only approximate in many cases, and also because there's lots of data problems, data missing in setting up the system. Other terminology you'll hear is those one-dimensional and two-dimensional words, 1D and 2D, and I'll explain a bit more about 1D and 2D in a minute on the next few slides. And also, when I've gone through the explanation of 1D and 2D, you'll see that generally 1D methods are good for pipe flow and river flow, and 2D methods are usually good for floodplain or for very wide estuaries and things like that. But there are other approaches ranging from much simpler GIS types approaches, filling in volumetric analysis or a horizontal projection, through to 3D solvers, through to physical modelling, which still has a place, but a much more limited place now in flood analysis. So let's work through some of that terminology. So 1D, one-dimensional, what it really means is it's solving the equations of flow using a 1D approximation. And 1D means it's usually means it's averaging all the parameters at one location, so it can average the cross-sectional flow through a cross-section in a river or in a pipe, and it's just using that average value, whereas the 2D approach will look at it varied in the X and Y dimensions and the horizontal usually. It's also used to cover a range of, I'm going to call them point features, which generally things that have got very little distance associated with them, such as weirs and bridges and sluices. Now, there's a whole host of these 1D point features that are useful or necessary when you're doing modelling. On the screen at the moment are an example of the 1D point features that are in the Flood Modeler software, which is the software from Jacobs. So in here, there's various types of weirs, river cross sections, various types of culverts, junctions, manholes, ponds and reservoirs, various types of boundaries. So tell the model how much water is coming in or out of that boundary, including a lot of hydrological analysis within there. There's bends, there's pumps, more weirs and sluices and siphons and blockages. All those could be considered as 1D elements within a 1D model, or 1D elements within a 2D model. So let's explain a bit more about that definition of 1D. So on the screen at the moment is a very simplified plan view of a channel, looking down on a channel meandering across my page here. If we take a 1D approach to that, what we do essentially is survey the cross section of the river, say every 100 meters, and those that can be at those locations where the grey lines are, and then we do a calculation at each one of those grey lines. That's what the orange dots are meant to represent, where we're assuming that we only do an average calculation. So it's the average flow through that grey line and a single water level through that grey line, which can be represented by the orange dot. So we're calculating everything at 1D, 1D averaged information at these points along a river cross section. Essentially, that's what a 1D model is. Now you can extend this 1D approach from the channel onto the floodplain, and that's what the grey lines on the screen at the moment are showing, where we've now surveyed out onto the floodplain, both to the left and right of the actual channel, and we can model the flow of water down both the river and the valley using the same sort of 1D approach. So with this, we'll only, on each one of those grey lines, we'll only have a single water level all the way across there, and we've probably got a sort of an averaged flow rate through the whole of that cross section underneath the grey line. Another sort of extension to this 1D approach, another way of representing flow on the floodplain, is to have what are called flood cells or reservoir units on the floodplain that are essentially a data set telling you the ground level against elevation, the ground level against surface area, building up a table to represent sort of a storage cell underneath one of those 1, 2, 3, 4 areas on the floodplain. Now what happens now is when water, perhaps at the start of an event, water's within channel, it goes down the river. As the water level rises up in the channel, it then may start to flow over those red lines, which are the top of bank, and then will start to fill up these flood cells, these buckets, if you like. So the model is allowing water to tip onto the floodplain and also to come back from the floodplain into the river, perhaps during the recession of the flood. So this is still a 1D approach, 1D cross sections in the river, and then a 1D flood cell type approach on the floodplain. So they're the key elements within a 1D model. 1D models are usually very, very fast to run, can take seconds or minutes. They're quite good at representing the in-channel water levels and flows. They're good at some of these point features, bridges and weirs and sluices, and working out the head loss, difference in water levels either side of a bridge or a weir or a sluice, and the flow through it if there's multiple routes through there. They can be good enough for representing the flow on the floodplain as well, although they're not, it's not one of the key parts of them. The things against using 1D modeling is that it's you need to know which way, you need to have some idea which way the flow could go before you set up the model. If you're setting up a model for a complex system, it can be quite time consuming to set up all the connectivity and the cross sections and these reservoir units of the system, and they can be poor at modeling the flow routes on the floodplain. So you can get poorer quality flood depth grid, flood extent information from it. And this is where 2D modeling really shines, in that it's really good on the floodplain. So 2D, 2 dimensions, it's solving the equations of flow in both if you're looking down on a bit of paper, for example, in both the X and the Y, the easting and northing directions, it calculates the flow in both of those, probably with an average, if it's 2-dimensional in the horizontal, it then uses an average calculation in the vertical. So for each little square where it does the calculations, it will have a depth averaged velocity and a single water level probably within the calculation area. What it does need on the floodplain, it needs a good terrain data, which DTM is the terminology for digital terrain model, or digital elevation model is another term used for something similar to that. So we need to know how the ground varies on the floodplain at quite a high precision. And if we're modeling in 2D within a channel, we need to have a good knowledge of the continuous shape of that channel, which is called the bathymetry of the channel. So here's a really simple square grid 2D model for the same floodplain and river that we saw previously. In this case, I've got using little squares. I don't know what these are. Say they're 10-meter, 5-meter squares everywhere, and the software will calculate the flow initially through the channel, for example, and then as it spills out onto the floodplain, it can then go. It can take a route connecting any of those little squares from the initial wet part to find a route across the floodplain. So on the picture on the right-hand side of the screen at the moment is showing an example 2D flood map. So you can see I've chosen one where you can actually see the squares that make up the grid here, the calculation grid, and you can see the darker blue is the lower parts within the terrain that have got a deeper depth on the floodplain and the main sort of flow routes across the floodplain. And then you can't quite see these, but there's little orange arrows on there, and they're the velocity vectors showing the direction of flow at this particular instant and that this snapshot of the flow across the floodplain was taken. So these are typical results from a 2D model of the floodplain. So what's good about it? Well, you don't need to define the flow routes. It will work out the flow routes based on the hydraulics and the topography and the roughness of the terrain. It is easy to set up, particularly for these square or constant grid sizes. It's very easy to set up. Another type of 2D model is where you have a spatially varying mesh. So triangles all varying in size and direction. They're a bit harder to set up, and you need some tools to help you set up to generate these meshes when you've got a irregular mesh. 2D is likely to be more accurate. Depends on the grid size. If you have a really big grid, sort of 50, 100-meter grids, it could be less accurate than 1D, but generally the type of grids people normally use means that you'll get a more accurate model on the floodplain than you would from a 1D representation. It directly calculates the variation of the flood depths and the velocities on the floodplain, whereas in 1D models you've got to do that as a post process to calculate that. What's against 2D models? Well, they can be slow to run. There's a lot more, lots more calculations it's doing, so it's slow. It can slow things down. There's various methods that software providers use to try and speed it up, but generally they are still slow. They're not running in seconds. They're running in minutes, hours, days, and even weeks for some of the big 2D models. They can be poor at representing some of the point features and channels if the channels are narrow, because you need to have a very fine mesh within the channels, which would then mess up the mesh everywhere else. So they're less good in these the point features in the river flow in some cases, and that's why linking together 1D and 2D modeling is so is generally the best way to do things in many cases. So what it's using is the best bits of the 1D and 2D. So it's using a 1D model for the channel and for some of these point features, and using a 2D approach on the floodplain. So going back to my sort of noddy plan view of a river going across a floodplain. So as you can see here, we've got the cross sections within the channel been representing things in 1D, and then on the floodplain we've got our grid, and we're doing 2D modeling on the floodplain. So it will, as a hydrograph comes in, say from the left-hand side of this image, it will flow down the channel. When the water level is higher than the bank, the red line, it will then push water over that bank onto the 2D grid, and then we'll start to spread the water onto the floodplain, and then it could go back into the 1D model somewhere else, either downstream or during a recession part of a limb, for example. So that's some of the terminology, 1D, 2D, linked 1D, 2D, and I want to say a little bit about the process of flood modelling. I've simplified it down to these 4 key steps. The first step is to work out, for the objectives of what you're trying to do, what is the best modelling approach. Then it's to make sure you've got all the data that is necessary, and you start building up your initial model. Once you've built up your base model, you then need to do some testing on it, check that it's running properly, to calibrate it, to try to make it so that it's closer to observational data, and then validate it, which is then to prove that for other events, it can still suitably, adequately simulate reality. And possibly also within there do some sensitivity runs, so you understand how sensitive the model is to various parameters or input data sets. And then when you're happy with, you understand the model, it's good enough for what you need, you then go on to the production runs. And those production runs could be producing flood maps for different return period floods and exceedance values, could be to have a tool you then run in real time during a flood to help drive the flood forecast, the flood warning, or it could be to assess different intervention options and appraise which go forward. And they're all part of that production run, step 4 part of this process. I want to say a little bit more about some of those steps. For me, the most important one is the first step, which is selecting the best modelling approach. And it's this is where the skills needed are, in my view. You need experience of doing some modelling to understand the data. You also need experience and knowledge of the location, so you can understand what are the locally important flood characteristics. You need to understand what the objectives of the project are. So if you're doing a flood forecasting project, for example, you need your model to run very quickly, which could be 20 seconds or something. So that again drives you towards a certain approach. You need to know what data you've got available. You need to know how much money and how much time you've got available to do it, because there's you don't want to spend all of your budget on setting up a model and have no budget available to actually do the simulations. And then you need to think about who's going to be doing the work and what software, what skills they've got available. And it's thinking across all of those 6 items really helps you understand what's the best approach. Now, there are some general sort of rules of thumb of which of these 1D or 2D approaches is going to be most appropriate. So if you're doing flood forecasting, usually it's the case that runtime or speed of analysis is the most important thing. If you produce a forecast a week after the event has occurred, it's a waste of time. You need to be able to get your predictions of rainfall and flows and then run your model in a very short period of time, 10 seconds, 20 seconds, a minute, a few minutes, and then that will enable you to do some work on it and then actually get the warning out so people can do something about it. So in this case, speed is important. If you can run the model in real time, 1D approach is what people tend to use. You can use 2D if you run a host of 2D runs beforehand and then use some lookup tables in real time to just find a pre-calculated, the nearest pre-calculated 2D run, for example. For flood mapping, if you're looking for accurate flood mapping in the UK, at least, most people are using these linked 1D, 2D models. So 1D for the river or the pipe network, and then 2D on the floodplain. There are cases where 2D only modeling can be used for flood mapping, and that can be definitely the right way forward in certain circumstances. But you still need to understand how you can route the channel, route the flows down the channel if we've got a fluvial system, and deal with those the local effects within the channel, which could be weirs and sluices and bridges and things and that, such as that, which could affect the flow rate down the channel and on the floodplains it happens. If you're doing studies to try to work out how best or what the options for controlling a sluice gate or a barrier or something like that, and then it's likely that a 1D approach is going to be most appropriate. You're going to be less interested in the floodplain and more interested in water levels and flow rates in the channel, and being able to run lots of options of control scenarios for those particular structures. 1D generally comes out top there. If you're looking at design for structural responses, so putting in bypass channels or pumping stations or barriers or sluices or embankments and walls, then maybe you want to try you need to use a few different types of model as you work your way through the process. And it may be that a simple 1D or simple high-level 1D, 2D model may be good at the start, and as you work your way down towards the appraisal and the final design, you may need more detail. But generally, we're talking about 1D, 2D linked models for most things within the design and appraisal of structural responses. Then finally, if you're doing a breach analysis, you want to know what area would flood if there was a failure in the embankment or the wall here. In that case, it's usual that a 2D only approach is probably all you need, because you may not need to calculate that. You've already got calculations of what the water levels or flows in the channels are. Data requirements. So again, these vary with the approach and the objectives of your study, but I've listed out a few of the basic ones here, the most common ones. So for 1D models, you need cross-section shape of the channel. If you're modeling the floodplain in 1D, you also need the cross-section across the floodplain. If you're doing a 2D model, if it's full 2D within the channel, or for example, with an estuary or something, you need to have the full bathymetry of that. You need to, for these point features, bridges and sluices, weirs and these sort of things, you need to know what type of structure it is, some dimensions for them and some coefficients, discharge coefficients, etc. for those, and you need to have control rules where there's something that moves on it. On the floodplain, you need to know the topography. So usually that's driven by grid data from something called LiDAR or from other forms of remotely sensed elevation data, although it could be a ground survey as well. But in the UK, at least, a lot of the time we're using LiDAR data to deliver that topography information. But on the floodplain, there could be other linear features that may not be captured very well in the LiDAR. These could be in roads or embankments, railways and embankments and things like that. So it's important to capture those as linear features and impose them on the terrain data. We need to know how rough the channel and the floodplain is. So if there's a high roughness, then it's going to slow things down, higher depths. If it's a very smooth surface, you can have lower depths, faster flow, and it can vary. The roughness can vary both within the channel and around the floodplain. So we need to have some information on that. And usually we can use sort of land coverage information or photographs to help with that. Boundary conditions are the things that drive how much flow goes into the system and defines the downstream usually the downstream boundary, which could be a water level or a rating curve, which is a relationship between flows and levels. And then we should try as hard as we can to get calibration data, because I say this is only a model, it's only a representation. We want to know how good the model is. We want to try to improve the model perhaps by varying the roughnesses to make it closer to observation. So obtaining observational data on previous flooding is really useful, really important, and you can use that to calibrate and validate your model. Very important in modelling is to spend time checking your results, because I said it's only a model. So there's various tools and methods you can use for that. We're looking at graphs, mass balance, convergence, comparing observations, and looking at the general credibility of the results. With modelling, there's likely to be iteration in that very rarely do we just run the model once, get the results and walk away. There's usually some process. Oh, could you try that? Or that doesn't quite look right. And then you go in and vary the parameters, vary the run, vary the event, and see how that affects things. Because these models are being used for multiple things, it's important to have good documentation and audit trail of why this was done. Managing all the different data sets is important, and treating the model as an asset so that it can be handed over to someone else and they can reuse it and have faith in it. We're finding a growing demand for modelling. More and more detail is required, and more scenarios are being asked for in modelling, and that has an impact on how we do the work. So I want to just finish off the last few minutes by giving an overview of an example of one of these flood modelling systems. I'm going to choose the Flood Modeler software, which is a product from Jacobs. It's been built, it's been in constant use and development for over 40 years, although the current user interface to it is only in the order of 5 years old. It deals with river modelling. It's got 2D, 1D, water quality, sediment, hydrology, links through to third-party software such as TwoFlow and Swim, for example. Is in the UK, it's the dominant river modelling software, and is used in over 100 countries worldwide. So, as I say, I'm just using this, just give an overview of this to give an example of what a modelling system could look like. This is a screen grab of the Flood Modeler main interface. You can see at the top there's a series of what we call ribbon menus, where we group together various types of menu buttons, sort of zooming in, zooming out, that sort of thing, turning on, turning off layers, tools in there to help you build 1D and 2D models, to do hydrology, to run simulations, and then to look at the results. In the main, the biggest bit in the middle of the screen there is of a GIS type view of, in this case, a 1D model, quite a complicated 1D model as it happens. And then on the right-hand side, there's some tabulated information on what makes up that model. A screenshot of a different model. So this is, again, within Flood Modeler, a GIS type view in the middle. This case is a linked 1D, 2D model, 2D on the floodplain, and then those black dots represent where there's a 1D calculation of the water level in the channel. And in this case, although it is only 1D, you can see we've generated, in a sense, a water surface grid within the river, and we've got the flood depth grid on the floodplain. Then on the right of the screen here is just some of the toolkit that's available within flood modelling. I've highlighted one which allows you to do a calculation of how long each grid square was wet for, to give you sort of a spatially varying event duration grid. And then finally on Flood Modeler, I've just almost randomly picked up some screen grabs of different parts of the software, just to give you a little feel of it. So the top left here is a data entry screen, for a asymmetrical culvert unit. Then on the top right is one of the toolkit in Flood Modeler to help you automate the process of calculating flood damages. So what would be the impact in pound sign for properties if there was a flood of a certain amount? And it goes through and does all that calculation for you and calculates, does it for different return period events, annual exceedance probabilities, and then comes up with a annualized value and a net present value damages value that can help you with an appraisal. Bottom right is a flood map with I think this is a Bing aerial imagery behind. So Flood Modeler directly links into these cloud-based imagery, satellite and OpenStreetMap and this sort of things, to help you get a feel for where in the real world the units that make up the model are, and that type of thing. Bottom left is a sort of a traditional time series plot. In this case, I've chosen 4 different locations within the same model, so you can look at all those at the same time. And that's what I wanted to go through. So to sum up, I've explained why flood modelling is very important, as it underpins so many aspects of flood management. I've talked through some of the terminology and the ranges of approaches, 1D and 2D, and I've hopefully you can see that 1D, 2D tends to be the most useful, taking out the best bits from 1D and the best bits from 2D. It's not always the most appropriate approach, but for many cases, particularly for river flood modelling, 1D, 2D approaches tend to be the most used. A key step in the modelling process is to select the modelling approach, the resolution you do the work at, how much calibration you're going to do, and this sort of thing. So planning the work is really important, and it depends on a range of things, primarily the objectives of the study and sort of the flow characteristics in the area, but also a series of other things such as availability of people who know how to use these tools. Then I went on to just give a quick introduction to a really high-level introduction to one of the modelling software that's out there. I've used the Flood Modeler software from Jacobs as the example. I've said that it includes 1D and 2D and linked 1D, 2D approaches, links through to other software such as 2Flow and Swim, and it's got loads and loads of productivity tools within it, within this sort of GIS type view, and that really makes it easy to set up your models, run things, spot problems with the model, and also to show the results to other people around you, other members of the team. The one thing I didn't mention actually during the presentation was the growth of cloud computing and how that's impacting on flood modelling. We've got a range of other webinars that do deal with this in more detail, but I just wanted to say that there's a definite move to doing calculations on the cloud within the suite of software we have at Jacobs. We've got a product called Flood Cloud that allows you to simply push Flood Modeler, 2Flow, another software, HECRAS, for example, models directly on the cloud, do the calculations there, then pull them back onto your local machine, pull the results back onto your local machine. And this is one of the ways that you can address this need for more and more modelling that's growing due to the benefits we're getting from using modelling and flood risk management for quicker modelling, more detailed models, more runs. Flood Cloud and using the cloud is a good way to overcome some of the hurdles of trying to do everything locally. And with that, I've come to the end of the presentation.